Alright kids, as soon as you're done with the test, you need to get through this video for Integration 4 and complete this homework for tomorrow. Tomorrow I will check homework Integration 3 and Integration 4. Remember that we will have our integration quiz on Friday, and that will be on Integration 1 through 5. So we will learn Integration 5 tomorrow. On Tuesday, Wednesday we'll practice. Thursday we'll move on to new topic, and Friday will be our quiz. But remember, the quiz will just be on Integration 1 through 5, not on Thursday's topic. So for practice, that does not have to be in your warm-up book. Let's integrate this function. This is a definite integral because I have x numbers here with respect to x. Now this is algebra. I could expand this. I could undo the square and say 16x to the fourth minus 16x squared plus 4 all multiplied, and then distribute the x's through that and just integrate piece by piece, which wouldn't be too heinous, especially because I'm plugging in a 0 here. So if you can think about why the second fundamental theorem would be okay, be pretty nice when I have a lower limit of 0 and I'm going to have every term have an x in it. But since we just learned u substitution, let's practice that. I'm going to make u equal to 4x squared minus 2, which means that the derivative of u is going to be 8x dx. When I look to substitute, I see that all of u is right here, and it's all inside the outside function of squaring, which I will be differentiating. But I see that I only need to replace x dx, which means I have too much information here. So I'm going to go ahead and move the multiplier over. Remember, you can only do that with numbers. Whoops, forgot my du. And now I have x dx to match right here, and I can directly substitute. So I'm going to copy the integral. I'm going to write down the u, copy the squared, and then substitute x dx, which is 1/8 du. I'm going to osmosis the 1/8 out here. So I'm just using my power up. Divide by the power up rule. So I'm going to get 1/8 u cubed over 3. Notice I didn't put my limits of integration up here because I don't want to put 0 and 1. 0 and 1 are x numbers, and this I now have an integral all in terms of u. So I can't bring myself to put 0 and 1 there. When I'm over here, I'm either going to not write 0 and 1 here and then replace the u with 4x squared minus 2 and then plug in 0 and 1, or what I can do is make the limits of integration u numbers. So I'm going to go to the u function here. I'm going to say, well, when x is 1, u is 2, right? 4 times 1 squared minus 2. And then I'm going to say, when x is 0, what is u? 4 times 0 squared minus 2 is negative 2. And I'm going to take these two limits of integration here, and then I don't have to bother to substitute. And I just have the second part of the fundamental theorem, and I'm going to have 2 cubed over 3 minus negative 2 cubed over 3. And that's 8 over 3 minus negative 8 over 3, so that's 1/8 times 16/3, which of course is 2/3. we could verify this. If that problem was ever on a non-calculator portion, you would not do that work. You would put the function in, you would put for x squared minus 2 all squared times x into y2, and then you would math 8. No, you wouldn't. You would math 9. Ah! From 0 to 1 of what was in y2 with respect to x. And a shocker, you get 2/3. Try to think about what you would do if you were using the u, right? You could try to put into y3, try to put u squared. I mean, of course you would have to put x squared. Put x squared dx times 1/8 and integrate that from -2 to 2. Oh, why is that a -2 up there? That should be a +2, right? Alright, good. Check. Now, this was review, and this is going to be a little intro into today's topic. As you saw in my calculator, I already had 1 over x into y1. Now remember, 1 over x is actually x to the -1, and remember, power up, divide by the power up, doesn't work when n is equal to -1, right? We established that before, right? Power up, divide by the power up. When the power up is n plus 1, this doesn't work. So how? But I need an integral of 1 over x. So I wanted you just to practice visualizing what's going on. Second trace 7. If you go, notice that I'm anti-differentiating from 1. So if I start at 1 and go to, what did it ask me, 1/8? I got -2.079. -2.079. Let's repeat that for a fourth. -1.38. How about a half? What do we get? -0.69. How about 3/4? You're about getting sick of this, aren't you? -0.28. Hopefully you know that f of 1 is equal to 0. And then what about 2? Hopefully you notice that going from 1 to 1/8 and then 1/4 and then 1/2, you weren't surprised that those were negatives because you were, right, dx or dt was negative, right? The function values were positive, but dt was negative, therefore you got negative integral values, and of course going from 1 to 1 gave you nothing. And then 2 gave us 0.69. And 3 this is our last one. Gave us 1.09. Now I'm going to do another thing with my calculator, just for fun. I'm going to hit my Stat button. I'm going to clear draw firstly. And I'm going to go to Stat and Edit, and I'm going to enter all the x values that we put into the accumulation factor. And I'm going to enter the approximations of the integral that we got. Notice I broke some AP rules here, and I didn't use 3 places past the decimal. And let me turn on my plots. And hit zoom 9. Now there is 1 over x. Let me go ahead and turn that off. How about just looking at the antiderivative values of 1 over x? Gee, there's an x-intercept of 0. As you go from, at 1, 0, as you go back towards 0, of which of course there would be a vertical asymptote, the integral values are getting more and more negative pretty quickly. When you pass the x-intercept of 1, 0, the y values do increase, but really slowly. Gee, what function does that remind you of? Wink, wink. Yeah. How about that? Oh, snap! Yes, it is true. The antiderivative of 1 over x is naturally ln of x. What? Now, before we write this down, this is kind of, let me go back actually. This is kind of freaking crazy. What we're going to do today is look at the antiderivative of 1 over x dx is indeed the natural log. I hope I don't freak you out too much by putting absolute value signs around that, right? Because 1 over x is defined for negative x's, right? Just not 0, and notice natural log is not defined at 0 either. OMG, math rules. But for 1 over x, there are negative numbers. So in order to use the natural log, if I want to put in negative numbers, I have to put absolute value bars around them, and hopefully that makes intuitive sense to you. But before I go on with practicing that, some common homework questions. I want to show you why I had both, I put both of these questions on, because they were very similar but take 2 different thinking processes. Hopefully for this one, you thought of sine of x being inside a -2, power of -2, with a cosine x outside, so that when you did u substitution with this, your u was sine, which made you happy because the derivative of sine is right here. So everything directly substituted. So if this was my u, and the derivative of u with respect to x was cosine x dx, this could directly substitute, no manipulation necessary, u to the -2 du, and of course integrating meant power up, so u to the -1 plus 1, I'm sorry, -2 plus 1 is -1, divide by -1, no limits of integration plus c, so of course I have to plug back in, so this would be negative u plus c. And of course, how can I check my work? Oops, sorry. Forgot my -1, didn't I? How can I check my work? Take the derivative. What is the derivative of negative sine to the -1? That's positive sine x to the -2 times the derivative of sine. And of course, that's what I have here. Check. This had the exact same denominator, so if you were tempted to say, oh, sine x to the -2, that's my u is equal to sine x, but when you went to take the derivative, which is cosine x dx, it's not there. That means you have to cross that out and try something else. There doesn't seem to be anything else to do with this. That doesn't match any formulas, so I ignore the calculus and just look at what I have. Ignore the calculus. Look at your integrand. Does that ring any bells? And hopefully that says to you, there's another way I can rewrite 1 over sine squared, and that is cosecant squared. Put your calculus back and say, does that help? And hopefully you see that it does, because this is right on your list, right? Somebody has a derivative of cosecant squared. What is it? Yay. Here is one that often kids have questions about. They're not sure what to do. They're like, ooh, do I make this my u? It is inside, and you're right, it is inside something to the power of 1. But if you make this your u, what is your derivative? Oh crap, I forgot my d theta, didn't I? What is the derivative? The derivative of secant is secant theta tangent theta, and the derivative of tangent is secant squared theta. All you have left to suck up is secant theta. That does not match du. You have to cross it out and start something else. So again, what I generally do is I say, well, ignore the calculus. What else can I do? I don't see any rewrites right away, but maybe, how about do some algebra? That's secant squared d theta plus secant theta tangent theta. I write now I match, don't I? Who has a derivative of secant squared? and who has a derivative of secant tangent. Tangent theta plus a constant and secant theta plus a constant constant is just tangent theta plus secant theta plus 2c, but 2 times a constant is still a constant. Hey, that looks just like that. Crazy, right? Alright, let's get back to our stunning revelation. Our power-up formula doesn't work when the power is -1. Whoa, my power's all gone. To integrate 1 over x dx, or x to the -1, so I recognize my power -1 means, uh-oh, we integrated, remember, 1 over x does not exist at 0. And we figured out that that was ln of the absolute value of x, because remember, to go, to use negative x's, which of course I'd have to redefine my lower limit of integration to be -1 instead of 1, I would get this. Now remember, the definition of this is the natural log of x as long as x is greater than 0, and the natural log of the opposite of x when x is negative. X cannot be 0, because x0 is not defined for the original integrand, and it is not defined for ln of x. This needs to go on your list, right? You have all your trig functions, well, a lot of your trig functions, sine, cosine, secant squared, blah, 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 and you have your power-up rule. Now you need to add the rule how to integrate 1 over x. So let's do these two. These are just going to take chain rule, right? This is 1 over stuff, right? You need to think about this as 1 over u to the first, right? Or u to the -1. So when I look at this, I say to myself, well, this is, I'm going to do this problem over here. If u is x plus 3, du is just 1 dx, right? So this is the integral of 1 over u du, which of course is the integral of u to the -1 du, which is ln of the absolute value of u plus c. So how about the second one? For the second one, there's something, this is a quotient. I don't know how to anti-differentiate a quotient. I've got to do something else. I see this fraction bar and I'm sweating, right? The first thing I think of is, well, that's not a derivative I can do anything with. I'm sorry, an antiderivative, because it's a quotient. I don't have any rules for anti-differentiating a quotient. So if I make u equal to x squared plus 1, the derivative of u with respect to x is 2x dx. When I try to substitute, my u is right there to the first, which is what I will anti-differentiate. Then I have x dx, and I look at my du and I realize I've got too much going on there. So I will move the 2 over, and I'll say 1/2 du is equal to x dx, so that I can, there's my x dx. So now I will say that the antiderivative of this x dx, remember, is du over u to the first, which of course is u to the -1 du, which is ln of the absolute value of u. Whoops, I forgot my 1/2, didn't I? So I have my 1/2, and then these again need to be u numbers, so u of 1 is 2, and u of 0 is 1. And I'm going to go over here. So 1/2 ln of the absolute value of 2, which of course is just 2, minus ln of the absolute value of 1, which is just 1. But what is the natural log of 1? That's just 0. So I end up with 1/2 ln 2, which AP could write as ln times the square root of 2, right? Because they would take this exponent up and that would be 2 to the 1/2. Woohoo! Now this fancy, remember tangent x was one of the things not on your list, right? This was not on my list yet. So check out this math. I'm going to use trig and rewrite it as a quotient. And now I'm going to, I can't anti-differentiate a quotient, but now that I know the stuff to the -1, I'm going to take that cosine in the denominator and I'm going to make it to the first power, and then I'm going to bring it up and make it to the -1 power. Then I'm going to, suck it up, and I'm going to make u cosine of x, which means negative du is equal to sine x dx. Float that negative out to the osmosis at outside. That's negative ln. Now I didn't use my absolute value signs, not yet, because I put cosine of x back. And the reason I didn't put the absolute value signs on yet is because I wanted to take that -1 exponent and put it on the argument, and then 1 over cosine, though, is a trig identity, which is secant, and now I will put the absolute value bars back up. This is the antiderivative of tangent, the natural log of the absolute value of secant x. Now, if you use this version is exactly the same. Is exactly the same, right? It is, but if you ever look up the antiderivative of tangent, this is the version that you will see, right? But there is nothing wrong with negative ln cosine of x plus c. It's just that, I don't know, I guess they didn't want to lead with a negative. So I could use that same kind of u substitution work to get you the antiderivative of cotangent, but I'm just going to give it to you. It's the natural log of the absolute value of sine. The antiderivative of secant x, which was not on our list before, is the natural log of, kind of gross, the absolute value of a sum. Cosecant is, shocker, the natural log of a difference. And notice that secant is secant plus tangent, and cosecant is itself cosecant minus, not tangent, but cotangent. Those are just little memory tricks. Now these antiderivatives on AP are not tested that heavily. We will test them on your quiz, we will test them on your Unit 6 test, but when it comes to May, these antiderivatives, they're just not used that often. They're not that famous. But you do need to put them on your antiderivative list to study. Alright, next objective. What function is its own derivative? Who do we love? Remember, I told you in Algebra 2 that you would end up loving this function. We love e to the x, don't we? Because it's its own derivative. So, will you be totally shocked to learn that the antiderivative of e to the x is what? Yep, e to the x plus c. Love, 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 love. So what do you think the antiderivative of e to the any constant times x? Remember, in derivative world, what was the derivative of e to the 5x? It was e to the 5x times 5. So what do you think the antiderivative of e to the 5x would be? Instead of multiplying by 5, divide by 5. So, do you remember when we loved e, but we didn't love, there's my broken heart, we didn't love 3 to the x. Why? That's pretty sad. Do you remember what the derivative of 3 to the x was? It wasn't just 3 to the x, was it? It was 3 to the x times, and this wasn't spitting out the derivative, right? Times, naturally, the natural log of the base. So what do you think the antiderivative will be? Oops. The antiderivative is 3 to the x. But instead of multiplying by the natural log of 3, guess what you do? Naturally. Right? Pretty cool. Of course, that I can chain rule you with, I can have some function inside the x, right? And as long as you have the derivative of the inside function to suck back up, you're all good. So in general, the antiderivative of any number, this stands, and this is important, this is not a function, it's any number raised to x is a to the x divided by the natural log of the base, excuse me. Those need to go on both of those need to go on your list, right? Your e to the x rule, e to the kx rule. This needs to go on your list, and yes, this is true for, right? If this was a to the kx, this would be a to the kx, klna, but of course, what could they do, right? Couldn't they make this a to the kx over ln a raised to the k, right? So AP will test your log properties. This is where they'll do it. Alright, so that's the end of integration 4. And so tonight, make sure that you pick up the integration 4 worksheet. It's kind of long because I did both general antiderivatives and definite integrals, definite integrals and indefinite. All right.